There are many different algorithms that we can use to plan paths through the environment. One of the simplest is called the potential field algorithm, and in this sort of simulation, in this algorithm, the entire world is sort of taken up as a representation of a surface where obstacles are large surfaces that stick out of the ground, and the goal is an attractive thing. So the idea here is that obstacles repel the robot, and the goal attracts the robot. And the robot sort of behaves as a rolling ball on this surface. So when it gets near an obstacle, it experiences a sort of oppositional force that pushes it away from the obstacle, all the while it's being drawn towards the goal. And that's kind of how this potential field algorithm works. There are a bunch of other kinds of planning algorithms, like graph search algorithms. You've probably heard of Dijkstra's algorithm that searches all of the possible paths before finding the optimal one. And there's also the A-star algorithm, which uses a heuristic to sort of sort the paths that allow you to get there. A-star is very commonly used for global planning in robotics. There's also random sampling trees, which is a way of growing a graph that searches through the state space sort of randomly, and we can sort the paths by optimal ones. Random search is very, very quick, so it's easy to find one, but it doesn't always result in an optimal path like Dijkstra's and A-star might. So let's look at the potential field algorithm in more detail. In this particular example, we have a very simple map where we have a starting location for our robot, and we have the goal for our robot, and we've got two obstacles. One is a little square and one is a little triangle. The goal generates a potential field map that looks like this, where the closer we get to the goal, the lower the potential force or repulsive force is. So a robot that starts up here would tend to move towards the basin that is the goal down here. Conversely, we also have a potential field generated by the obstacle. So here we've got our square obstacle and our triangle obstacle, and we can see that as the robot would get near these, it would experience a force that pushes away from them. We combine these, and now we have a total map where the robot should, if we have it set up so it behaves like a rolling ball, should be drawn towards the goal while rolling around the obstacles that are around it. The way this works is that if we have the robot and a goal, we represent the obstacles and the attractions as forces on the robot. So we might have a force that represents the goal, and we might have a repulsive force in the opposite direction that represents the obstacles. We do a sum of these forces, and that gives us a heading, that gives us a simulated force that we can use as our goal heading for navigating these things. So we would be driving away from the obstacle, but also somewhat towards the goal, and we might end up with a path that leads around the obstacle pretty quickly. It's not necessarily, the potential field algorithm does not necessarily lead to an optimal solution, but it is workable in most cases. Let's look at an example for our Project 5, where we'll be doing a GPS walls. So the idea here is that we build a polygon using the GPS locations and represented by latitude and longitude. These are just points, X and Y points in the world. We can use these X and Y points to generate lines. So we basically just take those points and solve for the slope and intercept of slope and y-intercept of these lines, and now we can do some manipulation with them. The first thing that we need to do is to figure out, given our robot's position, what are the intersecting points of the of our robot on those lines. So basically we want to find the closest point on our boundary lines that the robot is is near, and we can use that to determine how far away we are from that. And the way we do that is we take the equation of the line for one of our boundaries, and we take the slope from that and get a perpendicular slope. So a perpendicular slope gives us a line that's perpendicular, gives us a line that's perpendicular to the boundary line, right? Now, that perpendicular line can be anywhere along here until we define the intercept. So to solve for the intercept, we take the point that is our location. I want to find the line that passes through this particular location, which is our location on the robot. So the robot itself is one of the points. So we've got X and Y from the robot location. We've got the slope. We can solve for the intercept. And that gives us a perpendicular line, this purple line here, that we can use to then solve for the intersection point. So we've got two lines. We've got y equals a1 plus a1x plus b1, and then we've got our perpendicular line that passes through the robot. Then we can basically solve for the intersection point between those two lines. Once we have that intersection point, I can solve for the distance between my location and the intersecting point location, and determine whether or not we really care about that. We don't necessarily always want to be considering the boundary as a force on the robot. We might want to limit its effect. Otherwise, we might get some weird behavior from walls that are really far away when we don't really need to worry about them. But you also might notice that some of these walls, the perpendicular lines don't pass through the robot, or they might be outside of the bounds. Because this line would be infinite, it might be outside of the bounds of that line. So you have to check and see if we don't care about those, if we're too far away from the intersection with those lines, if it's out of range. So the next thing is, once we're within a threshold, we should calculate the force vector opposing that line. So the first thing we need to do is calculate vectors to our boundary lines. And the way we do this is by taking our current location and the intersecting point, and that gives us a vector, a unit vector, towards the boundary that we're currently examining. Then we want, because these boundaries are obstacles, we want to flip them around. So we create a force vector that pushes us away from the obstacle, and we then use those vectors to calculate a resulting vector by adding those up. This is a vector addition, and that gives us a heading that we can drive away from the location from. When it comes to obstacles, we want to do the same thing. Basically, we detect an obstacle, we calculate the vector towards that obstacle, then flip it around, invert the vector so that it's pointing away, and use that as a repulsive vector, and add up all the vectors between our boundaries, our obstacles, and the attractive vectors towards our goals, and that gives us a force vector that should help us navigate around any obstacles, while at the same time taking us towards the goal position that we want our robot to reach.